Why do we need another equilibrium constant? Why do we need Q? Okay, that doesn't use equilibrium concentrations. And that's because Q can help us predict which way the reaction is going to shift to equilibrium. Okay, so Q measures the progress of a reaction. So this is useful in the lab because you may test your reaction and get the concentrations, and you know what Kc is, okay, because lots of these have been tabulated for us, and you can look at what your Q came to be and compare it to what Kc is, okay? And then that can tell us which way, and then we can predict what's going to happen, okay? So this is the easiest way, I think, to look at it, okay? If Q equals Kc, okay, so if we do the math with Q and we have some concentrations, we plug it in just like here. If they're equal, that means we're at equilibrium. So if I go into any lab in here is running a reaction, I find the concentrations, and I know Kc, and they're equal, then the reaction is at equilibrium. Okay? If Q is greater than Kc, okay, so here's Kc right here in the middle. Right? So this is kind of a little, I don't know what you call it, graph-looking kind of timeline kind of thing here. Okay, Kc is in the middle. Okay, if we, at any point during a reaction, find that that Q is greater than Kc, okay, the reaction is going to drive to the left to get back to Kc, okay, because if it's an equilibrium reaction, they all have to get back to Kc, okay, at some point, okay. If Q is less than Kc, okay, so our equilibrium constant, then which way would the reaction need to drive to get back to equilibrium? To the right, right? So it's going to drive towards the products, okay? So if it's less, if we do a calculation and Q is less than Kc, the reaction is going to be shifting towards reactants to the left to get back to Kc, okay? And then if it's less, it's going to shift to the right, okay? So it's just a way to monitor a reaction, okay? So here's a problem here, and I may write out beside it, maybe some room there. If you have an equilibrium constant, that is 49, okay? So Kc equals 49. Okay? At 450 degrees C, you have 0.22 moles of iodine, 22 moles of hydrogen, and 6.66 of our hydrogen iodide there, okay? And it's in a 1 liter container, so we know we can divide all those moles by 1 to get molarity. Okay. Would this system be at equilibrium? Okay, so a chemist went in there, they found how many moles that they were using. It could have been their initial moles that they had calculated to put into the reaction. And we want to know, with those concentrations, is the reaction at equilibrium? Okay. So Q would have to be what to be at equilibrium? Equal to 49, right? Okay, so when we plug in these numbers, so of course we square it. Can't forget about that because we have a 2 here. Okay, this is the exact form of Kc, right, that we practiced on Tuesday. Okay, and we come up with 9. So our reaction quotient, think of it as progress of a reaction, is 9 versus 49, right? So it's less. Okay, so if we think about our Kc in the middle here, if Q is less than Kc, it's got to come back to Kc at some point. So the reaction is going to need to shift which way? To the right, right, to the products. Okay. Yes?
Is that something you might do more than once during a reaction?
Mm-hmm. Yep.
That kind of monitoring?
Yeah, because most times you want it to go ahead, especially in this situation, you want the most products possible. So you need it, if you're only at Q9, you need to shift it all the way.
Would you do something?
You could, yeah. You could try to speed it up. So heat, all the things we talked about, catalyst, you could try that. There's other things, tweaking all kinds of conditions, different solvents, different. But yeah, you want it to get to Kc. But once it gets to Kc, that's it. There's no more whatever products you formed. That's it. Remember, that's like we have a jug with water going in and water going out. It's still going to be moving at equilibrium. it's not going to hurt for you to leave that reaction running. It's just you're not going to get any more, right? Because once as much water is coming in as is going out, then and that equilibrium rate's the same, you're going to keep getting the same amount of product. Okay, so we're going to use this idea, okay, of Q again, but right now we're going to go and we'll see how we'll throw Q back in here to monitor a reaction. Okay, but we're going to talk about disturbing a system at equilibrium. So system meaning our reactants or whatever our reaction is that we have set up. Okay, Le Chatelet's principle, we will use this, I think, almost every chapter from here on out. So it will be on every single test. So you will want to be sure, obviously, that you know what it is. So today is a very important day with respect to this class. Okay, what it says, what it states, is that if a change of conditions or you stress your reaction, okay, we consider that a stress. Okay, everything's going all great and wonderful, and then you stress it, meaning you add more concentration of reactants or products or whatever. You change the temperature, okay, or you could change the pressure. Okay, there's different things that you can do to a reaction to stress it. Sometimes it's good stress. Don't think of it as negative. You can stress a system and it helps produce more product. So that's typically what we're aiming for, and we're going to look at a reaction where we do that. Okay, but if you stress a system, the system responds, your reaction responds in a way to reduce that stress. Okay, kind of like humans, right? We try to reduce the stress that we have. Okay, so if you're stressed, you're going to do something to reduce it. So that's what a reaction does. Okay, the equilibrium is going to shift, meaning if you stress it on the reactant side, then it's probably going to shift and put some of that stress on the product side. Okay, so it's trying to even it out. You kind of think of it as trying to balance. So the stresses we're going to look at, I think I just mentioned them, but one stress is concentration. So you've added a certain concentration, but then all of a sudden you throw in some more. So that's another, that's a stress. So you can add reactants or products. Okay, you can change pressure and volume. Okay, you're essentially changing concentration as well, but also you can change the temperature. So these are all stresses that can benefit the reaction, depending on, or they can also not benefit if you don't use them correctly. Okay, but the main idea, Le Chatelet's principle says, if you stress a system in one of these three ways here, the equilibrium, your forward and reverse, is going to shift in a way to relieve that stress. So you stress the product side, it's going to try to shift and unstress itself or de-stress itself. Okay. All right, so let's look at the first one here. Okay, we've already looked at this reaction and already stated that the Kc was 49. Okay. All right. So if we change the concentration of one of our reactants or products, that's going to change Q. Okay? It doesn't change Kc. Okay? There's only one way that Kc can change, and we'll see that later. Okay, but Kc, remember, this is a constant. Okay? This doesn't change. Okay? But if we stress a system, Q changes. Okay? So think about this mathematically. Of course, if you put ones all here, that doesn't equal 49. Okay, but we're just going to pretend here we're not worried about this 49. And let's say that everything here we had 1 molar. Okay, so our Kc would be 1, right? Okay, but what if you added some hydrogen? It's in the denominator. Okay, what's your overall number going to be? Is it going to be greater than 1 or less than 1? When you divide by a bigger number? Yeah, it's going to be less than 1. Okay, so if you do that and you add more, you just made Q less than 1, right? Okay, because Kc, we can only plug in equilibrium concentrations. But if we stress it and we say let's double our hydrogen concentration, okay, then we're going to make Q less than Kc. Okay? So if Q is less than Kc, and we just stress the system, well, Chatelet's principle says that our equilibrium is going to shift in a way that is going to relieve that stress. Okay? So if Q is less than Kc, which way is it going to shift? To the right, exactly. So this is going to favor the forward reaction and shift to the right or to the product side in order to relieve that stress. Okay? All right, if we do the opposite, okay? So we haven't changed temperature or anything here, but this time we're going to remove some hydrogen. Okay? So if you make that number, so everything was 1, let's just pretend at Kc, okay? Even though that doesn't equal 49. Okay? And then you remove some, so let's say we now have a Q where Q equals 1 squared divided by 0.5 times 1. Okay? So we take half of this away. Okay? What happens when you divide by a smaller number into 1? Q is going to be greater, right? So if Q is greater than Kc, you know the reaction needs to shift which way? To the left. Okay? So that's the way the reaction, the equilibrium is going to shift in order to relieve that stress. Okay, so what was the stress that we were putting on both of these reactions? Concentrations, exactly. So that's our first stress. The first one, did we increase? Yeah, increased the concentration. And the second one, we decreased the concentration. Okay. By adding or removing reactants or products, so meaning adding or, adding more or taking away concentration of our reactants or products, this does not change Kc. Okay, Kc was 49, and that stays at 49. Okay. What happened was we changed Q, right? Okay. And we reestablished our equilibrium. Okay. So we saw that if we change the value of Q, it's going to go back and it's going to be unaltered with respect to Kc. It's going to shift its way back to Kc over time. And that time is just dependent on the rate of the reaction, if it's slow or if it's fast. All right, we can also change volume. Really, this is more pressure. So I know it's got volume there. But does anybody remember Boyle's law and what it states? Anybody? It related pressure and volume. I'll give you that much. It's a big hint. If you increase pressure, what happens to the volume? Decreases, exactly. So there's an inverse relationship, right? Okay, if you increase the pressure, of course, on a gas, of course, no matter how much pressure, I can't squeeze this solid, a table, right? Okay, so it has to be a gas. So we know our gases are, random in motion, and we know everything we've talked about has to be in the gas phase, right? Y'all remember that? Okay, so if we increase the pressure on a gas, so just like in a Coke, you have CO2 in it, right? You have a gas, and it's confined into that little container. Okay, so you're putting pressure on that gas into a bottle, okay? And as you increase that pressure, you decrease the volume of the gas, okay? But if you pop that lid off and you decrease the pressure, then what happens to the volume? Increases, exactly. Okay, with that, let's go ahead and talk about this. So if you have a concentrated, we're talking about gases here, if you increase the pressure, what are you doing to the molecules? You're pushing them closer and closer. Okay, so what do you think is happening to the concentration? It's increasing, right? So if you're pushing things closer and closer together, you're increasing the concentration. Okay, so if we increase pressure, decrease volume, we're increasing concentration. Okay, and then that's going to be, reverse. If you decrease pressure, you increase volume and decrease concentration. Okay, so all in all, these all go together, but if you increase the pressure, you increase the concentration because you're putting those molecules closer and closer together. All right, so here's a reaction here. Did it give us Kc yet? I don't think so. Okay, so we have products over reactants. We square it. Why? We have 2 moles exactly of our reactant. Okay. All right, if we decrease volume, we increase pressure. So we just said that, right? Decrease volume, we increase pressure, which means that we also increase concentration. Okay. What's going to happen if, this is all according to Boyle's law, is Q is going to end up being less than Kc. So we could plug this in or see that. But basically for this one, Le Chatelet's principle says that if you increase pressure and increase concentration, the reaction is going to drive to the side of the fewest moles. Okay, this one's one of the harder ones to remember. Okay, so if we look up at our reaction here, which one do we have the fewer moles? The reactant or the product? Product, right. We just have 1 versus 2. Okay, so you want to think of it, so you increase pressure and concentration, so really on this side, and so on the left side, so Q changes, but Kc does not. Okay, whatever Kc is a constant. And it's going to shift to the side of the fewer moles. Okay, so I'll write that up here. So we shift equilibrium to side of fewer moles. Okay. If we decrease pressure, increase volume, and decrease the concentration, which way do you think we're going to shift? To the side of the more, right? I don't know if you can see that, but you can write down. Yeah. It all still has to do with Q, but it's really easier just to remember it this way. If you're increasing the concentration, then you have double the concentration over here, right? So if you're essentially that's what you're doing by changing pressure and volume. So if you increase the pressure 2 times on this side, that you're stressing this side, right? So it's going to need to shift to the other side. Okay, so that's the idea, and we're going to keep going over this in a few minutes. Okay, so is that the same one? Oh yeah. So now we're looking at volume increase. So just what I just said. So same thing, volume and pressure are inversely related. So if you decrease pressure, you're also decreasing the concentration. Okay, because now your volume's getting bigger, your molecules are getting further and further apart. And so now Q is going to be greater than Kc. Okay, and so the reaction is going to shift to the left, and it's going to drive towards the side of the more moles. Okay. All right. The third stress is temperature. And like I said, we're going to practice all these. I'm going to show you kind of an easy way to think about all these too. Okay. The value of Kc does change. So this could be a great multiple choice question on an exam. When does, I don't know what I would ask exactly, but which stress will change the constant or change the value of Kc? Right? And that would be change in temperature. Okay, it's the only one. Okay, the other two, Kc stays the same. Okay, it's a constant. All right, so if we look here, I already kind of answered the question, but we have delta H is negative. So does that mean it's endo or exothermic? Negative delta H. It's exo, right? That means that your heat value is on the reactant or the product side. Which one? The product, right? Okay, so if we wrote it out like this in our thermochemical equation, we would have plus 198 kilojoules. Okay, everybody see that? Agree with that? Okay. Basically, you look at this just like it's a product. I mean, it is, right? We did calculations with it. Even though it's not a compound, it's still part of the equation. Okay? So if you increase the temperature, okay, so the temperature here is on the product side, okay? Le Chatelet's principle says that if you stress one side, you're going to shift to the other side to relieve the stress. So think of it kind of like a balance. So if you really stress, so let's say we increase this temperature, okay, on this side, okay, then it's going to need, the equilibrium needs to shift back over to get this back to equilibrium, okay? So if you increase this side and stress it, you're going to shift the equilibrium to the other side, okay? So that's what's going on here. Okay. This one is to show you a catalyst that does not affect the equilibrium. Okay, so we said that a catalyst increases the rate of a reaction, right? Okay, and most all of you picked that and got that multiple choice question right. Some of you missed why, though. Why does a catalyst increase the rate of a reaction? Anybody? Some of you got it right. Yeah, it alters the pathway, essentially lowering the energy of activation. Some of you put all of the above, so you put that it changes concentration and changes temperature, all that. A catalyst does none of those. The only thing that it does is it alternates a pathway. So here's our energy of activation, okay? And now it's smaller. It's a different pathway. We have 2 steps, but it still lowers that energy of activation, meaning it's going to make the reaction go faster. Okay, but a catalyst does not affect equilibrium. Okay, the reason for that, it can make the reaction go faster, for sure, we know that, but it's going to make the rate of the forward and the reverse both go faster. Okay, so if you lower that energy, it makes the forward and the reverse go fast. There's no way for you to just make the forward. It would be a great invention if anybody came up with a catalyst that would do that, because then you could just use it just to make product, right? Hey, but it doesn't do that. It's going to make both rates speed up, but you're not going to get any more product concentration or any more reactant concentration. So it's not going to help with respect to equilibrium.
So it needs to like speed up the forward and disappear.
Do what?
It needs to like speed up the forward.
Yeah, you'd want it to speed up the forward
Evaporate.
and then not speed up the reverse. But there's really no way, to my knowledge, that you could do that. Okay, so all of these here, so we're going to do some practice here. But first thing I want to show you is when you're doing these, they all have to do with Q, like we're monitoring the reaction. Q, you use Q when you stress a reaction. So it's at equilibrium, and then you stress it. And then you can compare Q and Kc and see which way it's going to shift. Okay, but you can also look at this, and this is how I do it and how I learned it, is you can look at your reaction, and then based upon what's changing, you just think of it like I was showing earlier as a balance. And everything at equilibrium needs to be equal, balanced here. Okay, doesn't mean the concentrations are. Okay, but just at equilibrium, we want to think of it as being balanced. If you increase something, temperature or concentration, okay, they have the same really guidelines to go by, because your temperature is like a product or it's like a reactant. Okay, so if you increase one of those, you're going to shift the equilibrium to the other side. Okay, same idea, product. If you increase a product concentration, you're going to shift the equilibrium which way? To the left, right? Okay, so that's the same for concentration and temperature. Okay, now what happens if I lower the temperature on my product side? Which way do you think it's going to shift? Okay. Earlier we increased and we had to shift over here, right? Okay. If you have a loss, the equilibrium is going to shift to the side of that loss, right? So if I lose some concentration of products, I'm going to need to get it back up, right? So I'm going to have to shift the equilibrium back to the side of the loss. You'll hear me say this over and over again. If you increase concentration or temperature, you're going to shift to the other side of the reaction. If you lose any loss, you're going to try to compensate for that loss, and it's going to shift to the same side that you lost, whatever that is from. Okay? Okay. First off, we have another exothermic reaction. You need to recognize that that's exothermic, and that means that that 92 kilojoules is part of what? The reactant or the product? The product, right? It adds into the product. So let's go ahead and do that. Okay? So if we increase the temperature, so we're like this, okay? We're going to have to shift which way to bring that? Exactly. We're going to have to shift to the other side, okay, to bring that back up. Okay, so if you increase, you shift to the other side. So here we're going to be shifting to the left. Okay. And these are both, temperature is a great way to treat a reaction and try to tweak it and get it to work in the way that you want. Okay, if you decrease the temperature, okay, so now we're like this, what do we need to do? We got to shift over here and get this back up, right? Okay, so we're going to be shifting to the right. Okay. When you increase pressure, you decrease volume, and you make it more concentrated. Okay? So if you look here, how many total moles do we have on this side? Just look at coefficients. 4. Yeah, you've got 1 in front of the nitrogen, so we have 4. Okay, and then how many moles over here? 2. Okay, our rule states that if you increase concentration basically, so it comes back once again to concentration, you shift to the side of the fewer moles. All right, so which side has the fewer moles? The product. So you're going to shift to the right. So yeah, you could write product or right, whichever one you want. Okay. If we increase over here at hydrogen, which way do we have to shift to compensate? To the other side. So we're going to shift to the right. Okay. If we decrease ammonia output, then what are we going to? Which way are we going to shift to get it back up? To the product side. Yep. To the right. All right, what about a catalyst? How's it going to change equilibrium? So, I can't fit that in, so no effect there. Okay. Does anybody recognize this reaction from Tuesday? It's the production of ammonia. What did we talk about Tuesday? I can't remember. It was the process where the scientists won the Nobel Prize twice for it. So that was a while ago. Yeah, it's the Haber process, okay, where we take nitrogen and hydrogen. So I told you, this was a couple weeks ago, because we told you that you'll see this reaction, for the next few units. Okay, so we take nitrogen, which is really cheap, right? It's in our air, okay? So in our atmosphere. And you take hydrogen, which is also, okay, and react them together, and we form ammonia. Okay. We're going to come back to this, so I want you to look at these conditions. Okay, if you're running a reaction, which way do you want to shift the equilibrium? More than likely to the products. Okay, so look at our conditions. What would shift our reaction to the product side? Let's write those out. Okay, looks like we can decrease. I'm going backwards up the list. Okay, looks like if we increase hydrogen, okay. Okay, with that same idea, what else could we increase the concentration of that would shift the reaction to the right? Nitrogen, yeah. So it's just not one of our problems. But if you increase nitrogen concentration, you're going to shift to the product side. Okay. Okay, we can increase pressure. Bless you. Okay. Decrease temperature. Okay. And then we don't really like that first one, right? It goes to the left. Okay, earlier, and this was on Tuesday, I showed this reaction. I didn't mention that it was the Haber process. But our Kc, without changing anything here, just at room temperature or whatever it was, Kc was less than 1. Okay? Okay. He won the Nobel Prize not because he threw nitrogen and hydrogen together and made ammonia. It's because he made it efficiently. Okay? So it took a lot more than just throwing those together to make this reaction efficient. Okay? If you take away any changes here, then this reaction is not favorable. It has a Kc of less than 1, meaning that it's going to form what? Nitrogen and hydrogen. Okay? So what he was so brilliant was he went through all of these conditions and found certain conditions that make this reaction about 99% efficient, fast, and percent yield. Okay, 99%. Okay? So we're going to show it even more here later and talk about all the conditions. The only thing that you may think, right, look at this temperature. So if we decrease temperature, we're going to shift the equilibrium to products. But what do we know about the rate? What happens to the rate when you decrease temperature? Slows down. So that was kind of that's a negative at first for a scientist, because he knows at lower temperatures he's going to get more product, but he's also going to slow it down. Okay, so he has to compensate for that. Okay, and so we're going to see all of this put into one here in just a minute. All right, going to get my iPad back here. All right, that's what we just did. That's just the answers written in. Okay, work on these. Okay, you have one condition change. You have an increase in pressure caused by decreasing volume. I kind of erased it there. Okay, look at each of these reactions, A through D, and tell me which way is it going to shift, to the left or the right, or you can write reactants or products. If we increase pressure, we increase concentration. So we're going to shift to the side of the blank moles, more or less. Very good. What do you think? So we know we increase pressure, increase concentration. We shift to the side of fewer moles. So why? Why do we shift to the side of fewer moles? Okay, to balance it, which is what principle? Bless you. Le Chatelet's principle says that this is true because we want to shift to the side in order to relieve what? The stress. Okay, that's what a reaction at equilibrium does. If you stress it, it's going to shift to the side to relieve the stress. Okay. So the first one, what did everybody put for that? Okay, somebody put reactants. Anybody? Okay. How many moles are on the reactant side? 2. And how many moles on the product side? 2. Okay. It's not going to do anything. So you can increase pressure all day long and it's not going to help. It's not going to shift. Okay. All right. We have 9 moles on the left in B and 10 on the right. So it's going to shift to the left, fewer moles. Okay, we've got 2 on the left and 1 on the right in C, so it's going to shift to the right. And then we have 3 on the left and 2 on the right here, so it's going to shift to the right. Okay, had we done the opposite with respect to pressure and we had decreased pressure, then all of these would be opposite, right? Okay. How will an increase in temperature affect each of the following reactions? Okay, so B, you're already built in to your thermochemical equation. Okay, these, you're not really even given a number there, but it tells you XO or endo. Okay, and then here it tells you XO or endo. To the product side. Yeah. Yeah. And it acts just like it would if it was concentration. So you increase, you're increasing. Okay, so delta H is negative, so that means we're going to add heat to the product side. So we're not given a certain value, so I just put heat there. B is given to you, so you have the 92, so this is an XO. This one's endo, so that means we add 25 kilojoules to the reactant side. Okay, if we increase temperature, so over here our temperature is on, or our heat's on the product side, so we're going to shift which way? Right, if we increase to one side, we have to shift to the other. Okay. For B, same scenario, right? You increase, you got to shift to the other side, shift to the left. Right. If we have an endo and we increase, we're going to shift to the right. All right, what if we had lost heat on this one? If you lose heat, concentration, whatever it is, okay, you're going to shift to the side that you lost it from because you lost some, so you need to get it back up to be even. Okay, so we'd shift to the same side if we had lost heat. The first one's going to shift to the left. So left, left, right. All right, we've already talked about this quite a bit, but so we looked at the Haber process. We've actually looked at it twice in Chapter 17. Okay, it's still used industrial process in the U.S. and many other countries, mainly now for the production of fertilizer. However, it is used still for production, taking that and producing explosives to plastics, dyes, textiles. You know, it's used for a lot of things, household, cleaners, that kind of thing. Okay, so we already did this. Example 17.7 was that example that we just talked about and wrote this over here. So when we looked at that reaction, we wanted to find the optimal conditions to give us the highest yield of ammonia, right? Because that's what we want to produce. So if we look over here, I told you that earlier, I think it was example 17.5 or something like that, that Kc was less than 1 if we don't optimize our conditions. So it would mean if you just threw nitrogen and hydrogen together at room temperature, you're going to get back mainly nitrogen and hydrogen. So most people tried that, and then they said it didn't work, left it alone. So they didn't try to go any further. Okay, well, Haber did, and he found conditions that would optimize the production of ammonia. Okay, so we really are going to look at kinetics and thermodynamics here. So we've talked about kinetics. We know concentration changes, temperature, catalyst, okay, all those things, nature of reactants. Those all affect rate. Okay, so he wants it to be fast, right? You don't want to wait 2 days to sit there and, they're trying to, at this point, they're trying to bomb people. They need to do it quick. Okay, so you want it to happen quick and you want it to be efficient. So even, 50-50 mixture that's not good enough. You're not going to be in the 90s. You got to have 90% yield for something to actually be useful to people, especially nowadays. Okay. So we've already looked at this, but we talked about decreasing temperature. That's not really a great thing, right? Because if we decrease temperature, we also decrease our rate. So this is something we're going to have to try to compensate for. Okay. So what do you think we could add here that might compensate for the rate? What could you add to the reaction that might speed it up? Okay, no, we've got that one up here. Do what? A catalyst, yeah. It doesn't affect the equilibrium, right? It's not going to shift more to the products, but it could help compensate for the fact that you have to decrease temperature, which is going to slow down the rate. Okay, so he used an iron catalyst, which is really cheap. Okay, so that was a good thing. All right, what about this? So we said that decreasing our product concentration is going to make the reaction more efficient. Does that make sense? How are we going to decrease our product concentration? That's what we want to get, right? That's what we are trying to produce. So does that really, any ideas on that? How does that make sense? How could you decrease your product concentration and still form more product? Any idea? Okay. Well, the answer is, so if you look, so this is what we've just talked about, but we'll come back to it. This is kind of the commercial process. And what's done, we're going to talk about all the pieces here, but what they did here is they start pumping out the ammonia. So as it's made, they pump it out of the vessel, okay, and they have it in their hand, or in their container. But to the system, it looks like you're what? You're losing your concentration, right? So they have a pump that sits there and pumps it out at the same time it's making it. And so it decreases, in the system, it decreases your ammonia concentration just because you're sitting there and you're just pumping it out. But they're pumping it into whatever container they're going to go and store it or send it to wherever. Okay, and so it's made here, and then it's constantly pumped out. So that this keeps wanting to, so you keep pumping out what you're making, your product, which way is the equilibrium going to keep going? To the side of the loss, right? So if you keep pumping it out, it keeps making more and more and more. So that was one of the biggest things for this system and for the actual technique and putting together. So this is, of course, on a large scale in industry. So there are these big, huge, tall tower like things, and this is what's going on inside. But they have the, the big container that holds in the system, but then they have another container where it's pumped to. And so these chambers are huge, okay? So it just keeps pumping it out so that it keeps making more, okay? So that was a huge discovery there. All right, so we first start with heat, okay? So the reason we heat it at first, so the temperature is an issue for us. We want it to kind of be, we can't just increase it astronomically, because if we do, then we're going to shift our equilibrium the wrong way. But we can initiate some heat. It doesn't have to be done at room temperature, okay? And so we initiate some heat with a catalyst, right? Because the catalyst will help compensate for this temperature, okay? And then it goes through this heat exchanger, and then you stream in your gases, your nitrogen and hydrogen gas. Okay, so they're streamed in. They meet the catalyst in the heat, okay? And in this kind of tubing on top there, it shows where hydrogen reacts with nitrogen to make ammonia. Okay, that's what you want. All right? But then they have a cooling coil. What do you think the purpose of a cooling coil is? It's got two purposes. Decreases the temperature, so it's going to help drive your equilibrium to the product side. Okay, and then what else? Okay, how do you get a gas to a liquid? You cool it. Yeah, so you've got to cool it so that you can form liquid ammonia. Yeah. And then anything unreacted, so this is also nice, is that, you don't always get 100% conversion. So any nitrogen or hydrogen that was unreacted, it's not a liquid, it's still a gas. So it's going to flow back through here and go back through the cycle again so that it's not wasted. Okay? And then, of course, we still have our pump pumping out this liquid ammonia to continually keep shifting the equilibrium to the left. Yeah, I mean, especially back in early 1900s, and like I said, people looked at this reaction and they said that should make ammonia, but didn't make it efficiently. So that's as far as they went with it. Okay. Let's see what time it is, what we want to do. All right. We're going to do a little more practice, because this right here, so on Tuesday, this is the calculation I was talking about where it will take up your whole piece of paper. So, and you have a couple homework problems. It's really not that it's that hard. It's just you go through a lot of algebra. Okay, so all of you know what the quadratic formula is. Okay, so if you need to over the weekend, you need to look it up, make sure you remember negative b plus or minus square root b squared minus 4ac over 2a, and we're going to be using that. Okay, so it just calls for just being a little bit tedious. So we'll go through it on Tuesday and do all the pieces of it, and then we'll practice. Okay, so you need to have the calculator that you want for the test and be ready to be dialed in and keep up. So, but we're not done today yet. I'm just going back here. All right, so didn't show this because we talked about it over here, but this just sums up all the conditions for the Haber process. So tells us we have a dilemma with the temperature, so we use a catalyst, and we can also increase our nitrogen. So he did that as well, your hydrogen and nitrogen concentrations. Okay, it tells us at 25 degrees C the reaction's way too slow. Okay, so that's why we have to heat it, and it's even heated, pretty high. Okay, but we were allowed to compensate for that by using a catalyst and pressure. So we said over here, I forgot to mention that, increasing pressure. Okay, you have to be real careful with increasing pressure and adding heat, okay, to gases. So that's why, when you see an industry that have, those chambers are thick and absorbent and insulated. Okay, and then the iron catalyst is what was used, and that's really cheap. So a lot of our catalysts are really expensive, so they wouldn't be as useful in industry, but these are. So, we're going to look at just a few more problems, make sure everybody understands. Go to Blackboard real fast. Go ahead and show the homework too, just so everybody sees it. Let me check that date, make sure homework's due that day. Should be right. Now, you'll have a test coming up before you know it. Yeah. So your next test is October 9th, and it's just on Chapter 17. Okay. October 7th is when your homework's due. Okay, this homework right here, that's what we did in class. Or most of you even got almost done with it or finished it, so. Okay. All right. This worksheet, this is the one where I'd go ahead, if you can, print this off. This worksheet, that's why there's a whole space there, because we'll be doing these on Tuesday. Okay, and then there's another worksheet that's a little bit different. We're going to go ahead and go here. Okay. All right, I want you to look at this reaction and try to do numbers 1 through 5, and then that's all we'll do today. But just try to work these and see what answers you come up with. Okay, and that K, sometimes you just see that's KC or KEQ. So sometimes it's just written as capital K there. So yeah, number 6, I don't think. Yeah, number 6 is the long problem. We haven't gotten to it yet. So try to do 1 through 5 there. Does that help? You can see it. releases heat, so it's going to release it to the product side. Okay, if that was positive, you would add it over here. Right. Yep. Sorry. Number what?
Oh, sorry.
Number 2? No, that's exo, because it lost heat to the product side. That's exo. Mm-hmm. No, that's when it tells you, like, if it says delta H equals negative 1530, okay, if you look back at chapter 15, there's 2 ways to write these out. So I can either tell you that, or it can already be added in for you. But the main thing, an exothermic reaction releases heat to the product, so that's always exo. If this was over here, it's endo. If it gives you something like this, that means all that sign's telling you is exo. And so you would just add it to the product side. Yeah, if it was plus 1530, then you would add it to the reactant side. So if you decrease, you shift to the side that you lost it.
So it's going right.
So you lost heat, it's going to shift to the side that you're losing. Okay, because you're losing on the product side, right?
Gotta go.
So it's going to go to the right, yeah. Okay.
What about 3?
If you decrease the concentration of ammonia, okay, if you lose, you always shift to the side that you lose from. Mm-hmm.
Let's go to the left because that's where you lost it.
Exactly. Okay, predict the effect of adding more water to the reaction. There's water.
So
If you increase, it goes to the other side. Exactly. Yeah. So if you lose, it goes to the side you lost. If you gain, it goes to the other side. Mm-hmm. Yep. And then the pressure one is just, you got to remember, if you increase pressure, you shift to the fewer moles. And if you decrease pressure, you shift to so it's opposite. If you decrease, you shift to the side of the more moles. So it's just one you got to remember. Mm-hmm. Yes, to get all your concentrations, and then plug it in, and then square them, cube them, whatever. Yeah. Yep, and number 5, don't forget to divide by 5 liters, because you got to get your molarities first. Yes.
Square and cube them, but how do I know what's square and cube?
Oh, because that's your reaction still.
Oh.
Yep.
Okay.
You're welcome.
On number 5, since they're all getting divided by
5. Mm-hmm.
I just do it at the end.
I guess you could if you wanted to. I've never done it like that. I mean, I guess it would end up being okay to get your KC and then divide by 5, but I'm not sure. I mean, it probably would work.
Yeah, that's what I was thinking.
Yeah, you can do it that way and see if you get 62.1. Questions? Do what? Yep, we can go over them if we. Yep. Right. All right, if we increase pressure, we shift to the side of the fewer moles, which would be the left side, right? Because we have 7 moles over there and we only have 6 on the right. Okay, that plus 1530, some people are getting confused with that being a plus sign. Okay, when it's written into your equation, it's always plus. You can't have minus anything in your equation. But if it's on the product side, that means it's exo, because that's what an exothermic reaction is. It releases heat. Okay, so if you decrease the temperature of the product side, and if you lose something, what do you have to do? You have to shift to the side of the loss. So you're going to shift to that same side to get it back up, to increase the concentration. Okay. decreasing the concentration of ammonia. So ammonia is on our reactant side. So if we decrease it, we're going to shift to the side of the loss, right, which is our, the left. Left, right, left, and then if you add more water, so we increase. If we increase, we shift to the opposite side, right? So that's the idea. If you increase, you shift to the opposite side. If you lose, you shift to the side of the loss. That's the main idea. All right, you got to divide all those moles by 5 to get your molarities. You plug them in, you got to square it. You got to the 6th power, to the 4th power, and to the 3rd. So you can't forget to do that in your KC expression, and you should end up with 62.1 in the end. No units. Calculator. And do you have the form of it right?
I did those, the moles. I divided by 5 and got those. And then
Yeah, that's right. It's just, yeah. All right, we have lab Tuesday. You'll be doing your group 2 again, just doing the unknown. So really, I don't have anything to tell you on Tuesday. So I might even let y'all start a little early if we can. That way you can go ahead and get in there. But you're doing the same thing you did last time. So just wear proper attire and have a good weekend. Good weekend. Y'all have a good weekend. Bye. Have a good weekend. Y'all have a good weekend. Bye. Enjoy the pretty weather. Do what? I'm not scaling it. I know that much. We still have to wait on somebody to take it, so I can't give it back yet. So I'll let you know on Tuesday.
If you're going to scale it or not?
I'm not scaling it. I may let you correct your answers for a few points. Yeah. But yeah, it's not going to get scaled. Yeah. You'll have to work for your points. Yep.
I just didn't know what you were going to do.
Yeah. I can't give it back. We have somebody with an excuse that can't take it, so we will